You will all be familiar with the concept of static electricity, and it's a really important part of this syllabus. Now, there isn't very much you need to know, but it is a favourite question in exams. So before we start, it's worth just reminding ourselves what atoms are like. The centre of an atom, the nucleus, as you know, contains two types of particle. It contains protons, which are positive, and it contains neutrons, which are neutrally charged, so no overall charge, and it also has electrons, which zip around the outside. Something like this. So this is an atom of helium, as it happens. It's got two protons. So that's what an atom looks like. The interesting thing about an atom is overall it's got no charge, no electrical charge, because it's got, for every positive in the nucleus, it's got a negative around the outside. The interesting thing is that these electrons aren't particularly well attached. It's really hard to prize apart protons and neutrons. They really want to stay together. But electrons are really easy to remove, and they can be removed by something as simple as friction. If you rub two surfaces together, you can remove electrons. And that means what you leave behind, if you rip away electrons, you leave behind ions, which overall have a positive charge. And if you're stealing electrons and putting them somewhere else, then there you must be creating an area of negative charge. So you've managed to move around some of these electrons to create areas of positive or negative charge. Now, on an insulator is something that doesn't conduct electricity, charge can't escape. And so what you end up with is a build-up. You end up with this build-up of charge, and that's all electricity is in a static sense. Static electricity is just a build-up of charge on a non-conductor, on an insulator. That's all static electricity is. If you attached it to a conductor, well, the conductor, they provide an escape route. So electrons can run away. Metals, for example, are brilliant conductors. Electrons will flow through metals really easily. And so conductors provide an escape route or earth for the electrons to flow through. Now that's really useful if you want to avoid build-ups of static electricity. Conductors provide a way out. You may have seen, for example, a lightning conductor on the top of a high building, say a church spire, and it is there, something metal, so that hopefully when the spark of lightning hits the top of the church, instead of all of those electrons being crammed into one space, the top of the church, where they could do damage, they will flow down that conductor to earth. It's an escape route. It can get rid of the charge potentially when it's dangerous. Now, you should all know a few things about charge. If, for example, I manage to charge two pieces of plastic and I give them both a positive charge, then you should know they've got the same charge. They will repel. Same charges always repel. If I do exactly the same experiment but do it with two different types of material, and this time I have one that becomes positive because I steal electrons and another one that itself gains electrons, then I will have two opposite charges, and opposite charges will be attracted to each other. So you can see repulsion and attraction in static electricity. You can also see what we call induced charge. All this means is that a charge in one place can actually cause a charge somewhere else. Here's a ceiling, and here's a balloon that's just been rubbed on someone's hair. And as you know, you rub a balloon on someone's hair, it gets some static charge. So let's imagine that this balloon has become positively charged. I've stolen some electrons from it, and as I hold it close to the ceiling, well, the ceiling doesn't have any charge, but it does have electrons that might be able to move a little bit. And those electrons will come to the surface. They're attracted to the positive charge. And that leaves an area of positive charge up above it. And what I have in the middle here is a now negatively charged surface to the ceiling, a positively charged balloon, and so I will see attraction. So I could rub a balloon against my hair and stick it to the ceiling for hours. The ceiling didn't have any charge at the start, but I've induced charge by having a charge on my balloon. One other thing you need to be aware of that static can do, and I've alluded to this already, if you imagine a Van de Graaff generator and I get it very, very negatively charged, so I fill it with lots and lots of extra electrons. Now what that means is that those electrons are at a higher potential. They've got so much more energy. They really don't want to be close together. They really want to push each other apart, but there's nowhere for them to go. If I have something close by, an escape route to Earth, and this is our electrical symbol for Earth, those three lines, but I put something close to the dome of the Van de Graaff, you've all seen what happens. Just like lightning, a spark can leap across the gap, just like a little bolt of lightning. And all that is that the potential difference between those 2 points is so big that the electrons have enough energy to leap across the gap. And as they leap across, they make the air very hot, which is why you see a spark. This is a really interesting point from a safety point of view, because if you're refueling a vehicle, say an aircraft, or you've got a fuel tanker that's travelling for miles with liquid sloshing around inside, or an aircraft that's been in the air with air rushing past it, that's a lot of friction. That can move around electrons. You could end up with really big charges. Big charges, big potential differences equal sparks. And the last thing you want is you're pouring flammable fuel into an aircraft, or filling up the tanks at a petrol station from a tanker. The last thing you want with all of that flammable fuel is a spark. So you need to make sure that you provide some kind of earth, some kind of escape route, so that the electrons can flow away, so that you don't have too big a buildup of charge. Now, static is also really useful, and there are some common uses. We can use it to paint things. If I charge little droplets of paint as I spray them, if they all have a negative charge, they repel each other. So they don't want to be close. They push each other apart, and I get suddenly a very, very thin, even coat. Very efficient, very good coating. I can use them to remove smoke and soot particles from factories. So as the smoke rises up a chimney, it passes through some wires that are electrically charged, and that gives them a negative charge. I then have some positively charged plates on the side, and they're attracted to the side of the chimney instead of going up into the atmosphere. I can use static in a photocopier. I use something called a photoconductive material, something that only conducts charge when I expose it to light. And as I shine light on this charged surface, the charge disappears in the bits I want to be white, and the black lines that remain keep a charge that allows them to attract the toner particles. A really, really useful thing if we can use static electricity to attract things, to repel things. But we always need to be careful that we keep an eye out for where that spark might be a danger.